Okay, so get that,
Okay.
that today we're diving deep into something called SMaCk,
Okay.
which is
So
short for self-modifying code conflicts.
right.
And this is some pretty serious cybersecurity stuff, I got to say.
Yeah, no, it really is.
We're talking about a vulnerability
Mm-hmm.
that could even affect systems that you think are completely locked down.
Wow.
And our source material for this deep dive is a brand new research paper,
Okay.
straight from a top computer science conference.
Interesting.
So you're getting the inside scoop here, the
Yeah.
cutting edge of what's keeping cybersecurity experts up at night.
Well, and what's really interesting here is that
Yes.
SMaCk exploits how your computer's processor handles code
Okay.
at the very, very deepest level. It's not just about software bugs or missing patches,
Right.
but about how the hardware itself is designed.
So before we go any further, let's break down this whole self-modifying code thing.
Sure.
I mean, is this something programs normally do?
Well, actually, it's more common than you might think.
Really?
Self-modifying code, or SMC,
Yep.
is a technique where a program can actually change its own instructions as it's running.
So it's like,
It's like a chef tweaking a recipe while they're cooking,
okay.
to get just the perfect flavor.
I like that.
Yeah, and in computers, this kind of adaptation can lead to some serious performance boosts.
Right.
Modern processors are actually built to handle this safely.
Okay.
There are checks and balances in place, but here's where it gets interesting.
Yeah.
That careful handling, that's exactly what SMaCk uses against us.
Okay, so how does that actually work?
Okay.
I mean, we're talking about code changing itself.
Yeah.
How can that be turned into an attack?
Well, think of it like a safecracker,
Okay.
listening for the tumblers to fall into place.
Okay.
SMaCk is all about exploiting tiny variations in the way your processor works.
Mm-hmm.
See, when a program uses specific instructions to modify code in the processor's cache, think of that as the super-fast memory where your computer stores instructions. It actually causes a tiny slowdown,
Really?
almost undetectable.
Wow.
But it's there.
Okay.
SMaCk is designed to find and exploit these slowdowns.
Hold on, you said specific instructions.
Yeah.
Like what kind of instructions?
We're talking about things like flush store, even
Okay.
just a simple lock instruction.
Mm-hmm.
They're all designed to manipulate data and code in the processor's fastest memory,
Okay.
called the L1 instruction cache.
Okay.
But what the researchers found
Yeah.
was that these actions can be timed very precisely,
Yeah.
and that timing, well, that's the key to the whole attack.
So by timing how long these instructions take to execute,
Yes.
attackers can actually figure out what's going on inside the cache.
Exactly.
That's a pretty wild concept.
Yeah.
They're essentially spying on the internal workings of your computer.
They are. They're eavesdropping on the processor's own internal communications.
And that's how they create...
What's called a covert channel,
Yes.
a secret way to get information in and out.
Exactly, without anyone knowing.
Okay, I'm starting to see how this could be bad news.
Right.
But how do they set up those covert channels?
Well, the research paper focuses on two main techniques,
Go.
Prime+Probe and Flush+Reload.
Wow, those are some
Yeah.
interesting names.
They both use those tiny timing differences that we talked about to send secret messages within the system.
So instead of like regular data,
Yeah.
we're talking about bits of data being stolen.
Right. Maybe encryption keys or even sensitive files.
This is definitely getting into like things that keep me up at night territory.
Yeah. It's concerning stuff.
So it's not just theoretical, they've actually shown how this works.
Right. And that's what we'll get into next.
No, okay.
The researchers demonstrated how SMaCk can be used in real-world scenarios.
Oh.
We're talking about attacks on RSA encryption,
Wow.
which secures tons of online transactions.
And even vulnerabilities in secure logins.
This is getting serious.
It is.
But before we dive into those case studies,
Sure.
I think we need to take a quick break.
Okay.
We'll be right back with more on SMaCk and why this vulnerability is such a big deal.
Sounds good. Welcome back. So before the break, we were talking about
Right.
how attackers can exploit these timing variations
Right.
to create these covert channels.
Yeah, the covert channels.
Yeah. So let's take a closer look at that first technique.
Okay.
Prime+Probe.
Prime+Probe.
Yeah. Imagine a spy trying to send a message
Yeah.
using something totally innocent, like
our-
arranging books on a shelf.
Huh. Interesting.
Yeah. Their accomplice knows the code.
Okay.
So instead of books, though,
Yeah.
we're talking about data in the cache.
Right. Like chunks of data.
Exactly. And how it's arranged, that's the message.
So the attacker is like the sender then.
Right.
And they kind of set the stage, so to speak.
Exactly. They fill a specific part of the cache with their data.
Like setting up the pieces on a chessboard.
Yeah, a perfect analogy.
Okay, what happens next?
Well, then they wait, let the system run normally.
Okay.
And then the receiver, another malicious program.
Right, working with the sender.
Right, comes along and probes that same cache set.
Okay.
They do it very specifically.
Using those SMC triggering instructions.
Exactly.
Because those cause a slight delay.
Yes, if they hit the attacker's data.
So it's like a little signal,
Yeah.
slow equals 1, fast equals 0.
Exactly. And just like that,
Wow.
they have a secret channel.
Running right under the operating system's nose.
It really is quite sneaky.
That's an understatement, I think.
Yeah.
What about that other technique?
Great.
Flush plus IRLoad.
Flush plus IRLoad.
All right, how does that one work?
Well, that one's a bit different.
Okay.
It takes advantage of how programs share code libraries.
Like roommates sharing a fridge.
Perfect analogy.
Everyone can access the same stuff.
Right, so both the sender and receiver need access.
To that same shared space.
Exactly.
Okay, so they're both in the fridge, so to speak.
Right, and then the attacker, the sender, targets a specific line of code.
Okay.
Uses a cull flush instruction to force it out of the cache.
Like taking an item out of the fridge.
Yes, and putting it back in the pantry.
Okay, so the receiver's watching that item.
Exactly.
Waiting to see if it comes back.
And they use one of those SMC instructions to check.
So if it's back, that means the sender is communicating.
Exactly. It's a subtle signal.
Another way to communicate secretly.
Right, without setting off any alarms.
I'm starting to see why this is such a concern.
Yeah, it's pretty unsettling.
It makes you realize how much we rely on these systems.
It really does.
What can we even do to protect ourselves?
Well, thankfully, the researchers didn't just uncover the problem.
Okay, good.
They also looked at some solutions.
Okay, so what are we talking about?
Well, on the software side, one approach is constant time coding.
Constant time coding.
Yeah, it's like making sure every step in a recipe takes the same amount of time, no matter the ingredients.
So no timing variations to exploit.
Exactly.
Sounds complicated.
It can be, but there are tools to help. Raccoon, Escort, and Enclang.
I've heard of some of those.
They all help make code more resistant to timing attacks.
Like adding special ingredients.
Yeah, to protect the recipe.
But there are always trade-offs, right?
Always. Sometimes it makes the code slower overall.
To security versus speed.
Exactly. It's a balancing act.
What about the hardware side?
Right. Well, there are some options.
Okay.
But they come with their own challenges.
Like what?
Well, one option is to disable something called simultaneous multi-threading.
SMT.
Yeah. You might know it as hyperthreading.
Isn't that supposed to make computers faster?
It is, but it also creates the environment SMaCk needs.
How so?
Well, with SMT, multiple tasks can share the same processor core.
Like roommates sharing a workspace.
Exactly, and that sharing allows for information leakage.
Through those timing channels.
Precisely.
So if we disable SMT,
yeah,
each task gets its own private space.
Right, eliminating those shared resources.
So the attacker can't spy.
Exactly.
Right.
But of course, it can impact performance.
Another trade-off.
Always a trade-off.
Can we even detect these SMaCk attacks?
That's a tough one.
How so?
Well, SMaCk is very subtle.
Okay.
It doesn't trigger the usual red flags.
So our security systems might miss it.
It's possible.
So what can we do?
Well, the researchers found that monitoring certain hardware performance counters could help.
Performance counters.
Yeah, they trap specific events related to those SMC conflicts.
And we can see those tiny cracks.
In a way, yes, but it's not foolproof.
Right. Sophisticated attackers could hide their tracks.
Exactly. It's a constant arms race.
Between security researchers and attackers.
Always.
This is all getting pretty complex.
It is, but knowledge is power.
Right. The more we understand.
The better we can defend ourselves.
Okay, so we've talked about the technical details.
Yeah.
But what does this actually mean for everyday people?
That's a great question, and it's one we're going to explore next.
Okay, after the break.
Well, no, we'll just dive right in.
Oh, okay, great.
We'll look at specific examples of how SMaCk can be used to steal data, compromise login, and even bypass existing defenses.
It's a good reminder that the smallest details can have a huge impact.
They really can.
Okay, so we've talked about the technical stuff, those timing variations, covert channels, all that.
Right, but it's important to remember this isn't just theoretical.
Right, it has real consequences.
Exactly, so let's look at some concrete examples.
Okay, what's the worst case scenario here?
Well, the research paper highlights how SMaCk can be used to break RSA encryption.
RSA.
Yeah.
Like the cornerstone of online security.
The one and only, used everywhere.
From secure websites to banking, everything.
Exactly. So this is a big deal.
So we're not talking about some data leak here.
No, this is people's finances, personal information.
So how does SMaCk even do that?
Well, RSA uses complex math with secret keys.
Right, I remember that much.
And the researchers found a way to use SMaCk to reverse engineer those operations.
So they're like spying on the math itself.
In a way, yes. They observed the timing variations during decryption.
And that lets them
Recover bits of the secret key piece by piece.
So it's like figuring out the combination to a safe by listening to the clicks.
A very apt analogy.
That's scary, I mean.
It is concerning.
It feels like saying the math we rely on for security is broken.
Well, it does raise questions about those cryptography libraries we use.
Like OpenSSL.
Exactly. The researchers successfully targeted even the latest versions.
So even if your software is up to date,
You could still be vulnerable.
that's not a good feeling.
It highlights the need for multiple layers of security.
Right, not just patching vulnerabilities.
We need to design systems with security in mind from the start.
So it's not just about fixing problems after they happen.
Proactive security is key.
Okay, RSA is one thing, but what about other attacks?
Well, the researchers also demonstrated an attack on OpenSSL's implementation. The Secure Remote Password Protocol, or SRP.
That's for secure logins, right?
Exactly. You can log in without sending your actual password.
It sounds pretty secure. How does SMaCk break that?
It exploits a flaw in how OpenSSL handles certain calculations.
Okay.
And by measuring timing variations, they can leak.
What exactly?
The server's secret exponent, think of it as a master key.
So they could bypass the entire login process.
Potentially, yes, which is a major concern.
Sam, what's even scarier?
Is that it only takes a single trace of data?
So they don't need to watch the system for data.
Nope, they get what they need very quickly.
So we've got data theft, compromised logins, anything else?
Well, remember Spectre.
The vulnerability that took advantage of processor predictions.
That's the one. Affected tons of processors.
A big deal back then, still is, I bet.
And guess what? The researchers found a way to use SMaCk
To make Spectre worse.
to create a new variant. They call it iSpectre.
So it's not just a new vulnerability, it's amplifying existing ones.
Exactly, and it bypasses some of the Spectre defenses.
By leaking information through the cache.
Through the instruction cache, yes. And it works on both Intel and AMD.
So SMaCk can steal data, compromise logins, and make other vulnerabilities worse.
It's a serious issue, but knowledge is power.
Right. Understanding these threats is the first step.
And while there are no easy solutions,
Yeah, we talked about those countermeasures, like constant time coding.
and disabling SMT, but it's an ongoing challenge.
Security is a cat and mouse game,
Always has been, always will be.
but by being proactive and staying informed,
We can make it harder for attackers.
well, this has been an eye-opening deep dive for sure.
It's been my pleasure sharing this information.
It's important stuff. Cybersecurity is everyone's responsibility.
Absolutely, we all play a part in making the digital world safer.
Couldn't agree more. So for our listeners, stay curious, stay informed, and stay safe.
And until next time,
We'll see you then.
Thank you.